We've been doing the mean value theorem at university in the last couple of weeks, so I thought this was a good chance to do a video on the subject. So here are the three typical questions that you might see in a test or an exam. So let's go to the first one. And here it's just asking us to do some calculations. There's no need for us to do a proof. There's no need for us to even state the mean value theorem. I'll do that later in one of the other questions. So one way to look at this is to basically add a few words to the theorem. So I like to think of it as the mean average value of the slope theorem. Now by that I mean, let's look at the curve that we're looking at in this question for fx. If I asked you what's to draw on here the average slope, the mean average slope between 0 and 6, or between 1 and 6, then you would probably draw a line between this point and this point, and that would represent, without going into all the mathematics of it, that's probably going to be the best guess as the mean average slope. And what the mean value theorem says is that when we look at any point between 1 and 6, there must be a point where the slope at that point is equal to that mean average value. So down here the slope is less than the mean, up here it's higher than the mean, and somewhere around here there's going to be a point that's equal to the mean. So that's all we have to do is put that in some words and numbers. So here's one solution. The mean average slope is the rise, which is 6 squared minus 1 squared, over the run, which is 6 minus 1, which is equal to 7. Now, since the derivative of the function f at the value x is equal to 2x, it follows that at x equals 7 on 2, the slope will also be 7. And that would be enough to get you full marks. Before I go on, I just mention that I've got lots of other videos in this playlist where I go through typical university and late high school maths questions. I've also got some other playlists which has things like about the number e, formulas for pi, the largest number. Also got things like how JPEG, Google search, CT scans, encryption work. And I've got some other ones if you're interested in things like Fermat's last theorem or Poincare conjecture, prime number theorem. I've got some videos that introduce you to those concepts and some of the proofs. So have a look at any of them if you're interested. Now let's go on to the second question. This is a pretty typical question. Use the mean value theorem to find an upper bound on epsilon, where epsilon is the square root of 26 minus the square root of 25. So this has sort of got a bit of an engineering feel to it. Before calculators, if you imagine someone saying, well, what's the square root of 26? And you say, well, it's close enough to 5. And what we're doing here is saying, well, how close actually is it to the square root of 25, which is 5. So let's state the mean value theorem. It's a good idea in a test or an exam to actually state the theorem. If you stuff everything else up, you probably still get a mark or two. And sometimes by just writing it down, it helps you get started. So the mean value theorem says that suppose f is continuous on a closed interval AB, so that includes the points A and B, and it's differentiable on an open interval AB, so these are all the points between A and B but not including A and B. Then there exists a C that's an element of the open interval AB such that FB minus FA, that's the rise, divided by B minus A, that's the run, is equal to F dash C, which is the slope of the curve at this point C. So for a solution for us for this problem is we're going to let fx equal the square root of x. That's a logical thing to do. Let's let A equal 25 and B equal 26. Now the function f is continuous on the closed interval 25, 26, and it's differentiable on the open interval 25, 26. So by the mean value theorem, there must be a c in the interval 25 to 26, but excluding those 2 points, such that the rise between f26 and f25 over the run, which is 26 minus 25, must be equal to the derivative at the point C, and the derivative of the square root of x is 1 on 2 times the square root of x, so the value at C is 1 on 2 times the square root of C. Now we've got to find an upper bound on this error, which is this 1 on 2 times the square root of C. So the observation we have to make is for C anywhere in this interval between 25 and 26, it's clear that 1 on 2 times the square root of c is less than 1 on 2 times the square root of 1 on 2 times the square root of 25, which is equal to a tenth. So now if we go back and fill in f26 and f25, and also if we can work out that 26 minus 25 equals 1, then we have the square root of 26 minus the square root of 25 divided by 1 is less than or equal to a tenth. And so therefore an upper bound on epsilon, which is this difference between the square root of 26 and the square root of 25, must be 1/10. So that should be enough to get you 4 marks. Now the third one, and this illustrates a clever use of the mean value theorem. The one I've picked actually is quite a difficult one, but hopefully you'll get the idea. So here this is different. This is not working out an upper bound for an error like we had before. This is using the mean value theorem to solve an inequality. So up here we've got this inequality, and it's tempting to think of the mean value theorem here as being between pi on 3 and pi on 2, because that's what we've been doing so far, because that's what we're interested in this inequality. But what we actually have to do is think a little bit differently. So what I've done here, I've got this graph here where I've graphed the function, but down the bottom I haven't used x, I've used t. And I've used the two lines to show the pi on 3 and pi on 2 rising vertically up to intersect with the curve. Now what we want to consider the mean value theorem over is between pi on 3, which is the lower bit, up to this point, a point x, where x is going to be somewhere in this, somewhere between the two vertical lines. So that's what the mean value theorem is going to apply to. Rather than what our first thoughts were. So it's a little bit tricky, this. So what I've said is let ft equal sine t, and let x be just some arbitrary number that's in this range between pi on 3 and pi on 2. Now the function f is continuous on the closed interval pi on 3 to x, and it's differentiable on the open interval pi on 3 to x. So by the mean value theorem, there must exist a c somewhere in this interval between pi on 3 and x, such that now we use our formula, the rise over the run, sine x minus sine pi on 3, sine x minus sine pi on 3 divided by x minus pi on 3. So, sorry, I've explained this badly, this expression on the left. And that must equal cos c for some c that's between pi and 3 and x. Now we can use the trick that we used before to bound this cos c. We can say that cos c is less than or equal to half for any c in this range between pi on 3 and pi on 2. I'll leave you to work that out using some high school trigonometry to see that that's correct. So what we now can do is start to simplify the expression we had before with the rise over the run. So we've got sine x minus the square root of 3 on 2 divided by x minus pi on 3 must be less than or equal to half. And when we sort all that out, we get sine x on the left and the required answer on the right. And that's going to be for any x in the range pi on 3 to pi on 2. So that's the mean value theorem made easy. I hope you found it useful.